So like most revolutions, it didn't happen overnight. So these little tchotchkes were made by the 3D printers up on the 3rd floor. If you haven't seen them operate, you should. I think this is quite a remarkable thing. Don't know how long it took to build this up by successive layers, but it's pretty impressive. At last year's Idea City, we heard from Hod Lipson, who is a professor at Cornell's Creative Machine Lab. And he came to describe for us how a device that had been around a long time, laboring in obscurity, in unseen industry processes, was about to leap into consumer consciousness and revolutionize manufacturing. Also last year, as an expression of what might be done with this new technology, we heard from people who were developing artificial meat, actually trying to lay down cell structure to create a hamburger. Not everybody was thrilled with that prospect. So I want to continue that discussion today because a lot has happened in the intervening year. We will proceed in an orderly fashion. Our first speaker will give us a sense of the history of this device, show us what a 3D printer actually looks like, how it works, and then we will hear from a number of people about the kind of uses that they want to put this device to. People say, people predict that in a couple of years, 3D printers will be like computers. Everybody and every household will have one. So we'll begin with Liav Koren.
Hi. So I'm a Toronto-based designer and researcher and kind of creative technologist, and I've been working with 3D printers for a few years now. And I'm just going to sort of walk you through some of the history and trajectory of 3D printing so that you can kind of understand where it comes from and where it's going and what people are using it for, as Moses said. And just as a side note, something about this size, at a guess, would probably take 3, maybe 4 or 5 hours to print. So in the beginning, there was as with many things, you can sort of go back to the 19th century. And there was a fellow by the name of Benjamin Sheridan. And he, among other things, he was an entrepreneur, an innovator, an inventor, and an artisan. And he made his living as a sort of machine sculptor. We actually have a really lovely collection of some of Sheridan's work at the Art Gallery of Ontario. It's worth checking out. They're really beautiful pieces. And what they are reproductions. Sheridan had a mechanical system that allowed him to make these reproductions of some of the best sculptures and busts that were available in England and Europe at the time. He was working in the 1820s, 30s, 40s. And the device he was using was based on something that we now think of as essentially a children's toy. It's a device called a pantograph. And it looks more or less like that, the pantograph. It's used for reproducing and scaling two-dimensional drawings. And for centuries, this was really the only way that you could reproduce and scale two-dimensional drawings sort of easily and accurately. What Sheridan had was basically a three-dimensional pantograph. So the way this system would work is you would take an original and place it on the stand, and you would trace contours across the surface of this object. And there was a second stylus that was connected along the arm of this machine, and on the end of that second stylus was a rotating file. And this file would sort of mirror your movements in space as you're tracing contours, and you could kind of carve into alabaster or marble or clay and produce a roughed-in reproduction of the object, which was then finished by hand. So this would have been, as you can imagine, a really time-intensive and laborious and painstaking process. But it's what Sheridan did, and it's how he made a living and gained quite some acclaim for some time. The next really kind of major, or one of the next major kind of innovations or developments in the field that would become digital fabrication, the field of producing objects with computer-controlled tools, occurs about 100 years later when you actually get the first automated machine tool. This is sort of similar to Sheridan's tool in that it's, again, a kind of rotating file. It can engage a piece of material and carve away at it and produce an object. This machine, which was developed in collaboration with MIT and military aviation contractors in the 1940s, was shown to the world in 1952, and at the time, it was accurate to 1/5000th of an inch. Astonishingly accurate. And the only reason why it took 100 years to get to that point, essentially, is because they needed the control systems, both the theory of control systems as well as the actual mechanisms. And those had only really been developed properly in World War II for the use in automated gun mounts and radar mounts. In the 1960s, you get another major development, which is the first real CAD package, or CAD software prototype. You can see a demo of this up on YouTube. It's an astonishing demo. This gentleman is working on an oscilloscope display. He's drawing interactively in 3 dimensions with a pen, a light pen, into the screen. And the system has an understanding of spatiality. It understands that he's drawing a chair and that things are kind of linked together. So it has some intelligence to it. It's really a remarkable system, and it would be recognizable to anybody today who was using CAD systems. So by the 80s, with the first kind of wave of personal computing sort of beginning to move out into the world, all the major infrastructural elements were in place for digital fabrication to kind of take hold. And you get the people starting to work in the domain of what would become 3D printing. They work on the first problems, and the first kind of fundamental patents in the area are filed, and the first companies in the field are founded, sort of the mid to late 80s. And these companies sell 3D printers on sort of a mainframe model to large institutions for a large amount of money. And that proceeds for a while. And then in the 2000s, as these fundamental patents start to reach the end of their life cycle, you get what would become the sort of second wave of digital fabrication, and what would also become the founding of personal fabrication, personal 3D printing, with the RepRap project. So this is also a 3D printer, but it's a very different paradigm. RepRap stands for Replicating Rapid Prototyper. All of these machines are rapid prototypers, but replicating in the sense that this machine can print the parts for itself. All the white components and green components are 3D printable on a machine like this or a very similar one. Everything that isn't 3D printable is available cheaply off the shelf. So it's a very different sort of industrial design philosophy. And the other really different thing about it is that it's an open source project. We've already heard people talking about open source at Idea City. Before RepRap, RepRap was one of the first really significant open source projects. And in this context, open source means that all the relevant knowledge that you need to engage with this, to engage with the community, engage with the project, is available. The design files, the specifications, the bills of material, and all the relevant kind of theoretical knowledge can be kind of gleaned from the main website and the community that forms around it. So in 2008, the RepRap project achieves the first self-replication. This parent printer over here printed all the component parts for this child printer. And also in 2008, the RepRap project believes that the first commercial transaction of a RepRap occurred. That's myself, my buddy Mike, and an engineer by the name of Wade Bortz. His parts had been actually cast from master molds in England. And we bartered a case of beer for a shoebox full of 3D printed components. And so who was I at the time? I actually wasn't really a technologist. I'd worked with computers, I'd done some programming, I'd studied a modest amount of math. But really, I was an architect, or an architect in training. I'd attended the U of T's architecture program. And while there, that was really my first introduction to digital fabrication. I had access to a lot of really sophisticated tools, 3-axis milling machines, laser cutters, high-end commercial 3D printers. And I and my classmates began kind of exploring what these tools made possible, both in kind of conventional architectural projects, as well as in sort of much more abstract digital explorations. And what I sort of very quickly realized is that digital fabrication and these digital tools kind of allows you to engage in this very collaborative and exploratory relationship where you can set systems up or rules up, and you can kind of understand them very clearly at the beginning and still get very surprising results out. Something as sort of simple as a very rectangular grid of points, a very regular grid of points in space, if you achieve enough density, can become really interesting, kind of mysterious and seductive. And obviously, digital fabrication, digital tools allow you to work with orders of magnitude more density of information than you could ever do so before. So I was working as an architect, and I was also, in my free time, continuing to explore this world of open fabrication and 3D printing. And at a certain point, I had the opportunity to work with Beasley. He is a local architect, but really he's also an artist. And he's pushing the boundaries of digital fabrication within the context of contemporary art practice. He does these incredibly intricate, incredibly large installation pieces, both as permanent and temporary installations. And we were a team of architects. We were all architects. And we were doing these things that our professional training and really our discipline had not prepared us for in any real way. Every component in Philip's sculptures, or almost every component, is custom fabricated. And he's actually using even simpler technologies than 3D printing. He's using a lot of laser cutting for the most part. And it's this really intricate exploration of process and material, and kind of understanding just how much you can cut things apart and twist them around and then begin to link them together into these very large, sophisticated nets and meshworks and frameworks. And embedded through all of these installations and pieces and sculptures are sensors and motors and actuators and microelectronics that provide kind of rich interaction with people moving through the space and through the installations themselves. So what my world kind of looked like was not so much the big, drapey, dramatic thing, but more like this, figuring out how to deal with all these tools and the electronics and the componentry. And again, what we all sort of learned was that with this much more open access to the information you needed, as well as the tool chains, we could kind of get what we needed to find to be productive and achieve what needed to happen. So I was designing circuit boards, obviously not anything within my previous training. It's feasible now because you have the barriers to that body, those corpuses of knowledge are so much lower. And this is really one of the kind of key enablers in that revolution. This is an Arduino. It's both a physical computing platform. It's one of the, basically the kind of microcomputer that gets embedded into all these sculptures as nodes. There's dozens of them. It provides computation and some interaction. And it's an open platform. Both the circuit board itself is open and can be modified, downloaded, adjusted, reshared, as well as a software platform and a community. It's also interesting to note that it's actually built on a closed product in some ways. The big black rectangle in the lower right is the kind of brain, the microprocessor of it, and that's actually a closed commercial project. So open source projects can intermesh with closed products and projects in really interesting ways, and then can kind of bootstrap themselves in really interesting ways. So once I'd finished up with Philip Beasley, my time at Philip Beasley, I got this really interesting offer to join a local Toronto startup called Pendant Robotics. And we were trying to basically bootstrap a commercial 3D printer. So again, I was sort of engaging with a discipline I hadn't really formally studied. I had never done kind of product design or industrial design. And again, sort of able to learn what you need to just in time, in a sense, to solve the problems you're faced with. You know, I needed to figure out how to detail and put together an enclosure for a consumer prototype. And you could sort of do it. You know, 10 years ago, a proposition like Pendant Robotics wouldn't really have made sense. Today, you can bootstrap yourself. And what's sort of interesting to understand and take away is that 3D printing, digital fabrication, they're not likely to displace traditional manufacturing in the near future. What it is a really nice kind of supplement to it. It speeds up your design times, your iteration times, and allows you to go fast, 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 fast. And that's always kind of been one of the kind of killer apps for this field. It's sort of slowly starting to encroach into production and the kind of consumer space in really interesting ways. But its use in kind of the design cycle is really a kind of sweet spot for digital fabrication. So, I mean, we were quite successful in what we were setting out to do. We managed to put together a working prototype and got a lot of attention for it. That startup ultimately was not successful, but it was a really interesting experience. And digital fabrication itself is really interesting because, and 3D open access to bodies of knowledge is really interesting because it sort of promises to do for a whole range of disciplines what it's done for software and information technology. As we've already heard, this is kind of in the process of coming to biology and robotics. It's going to kind of encroach on many other disciplines, analytics, cultural preservation. In the previous slide, there was an example of people printing blood vessel networks using an open source 3D printer, which were then modeled and kind of populated with cells. There's a really interesting case study where this firm in the UK documented the disassembly for restoration of a 160-year-old locomotive that was quite unique. And they were able to do this both with 3D scanning, where they could capture, as well as 2D, just conventional high-definition photography. They were able to capture a huge amount of information about this locomotive and also kind of bootstrap a business for metal train kit enthusiasts that was crowdfunded. It's a really interesting case. And there's a huge amount of excitement and interest going on, obviously, within every gamut of the design field, from architecture to the design of prosthetics, where this child has been given a prosthetic limb that's been printed with an affordable consumer-grade 3D printer. So, in conclusion, I'm really honored to have been asked to speak here, and thank you for your attention.